Okay, so many of you can probably guess the next kind of active filter we're going to look at here is a high-pass filter. And so I've given you a circuit diagram of a high-pass filter, and again we're going to kind of just do a non-diving into equations approach, just kind of what I would say is a maybe more qualitative approach to this to see that this does give me a high-pass filter. So again, remember ZC is minus J over omega C, which we've said this many times, cap short for low frequency, cap is open for high frequency. So let's just think about this here for a second. I'm going to draw this in here and then I'll erase it here. So if this was a short, like that, I'm shorting out that resistor. And if you just think about, again, a simple gain equation for an op amp here, inverting op amp, my gain equation is negative R2 over R1. This is just not for a filter, this is just for the op amp, right? You know, assuming that we didn't have any capacitors or anything. But now if we short this R2 out, we basically just have a wire then connecting the output to the input, but a wire has zero resistance, so my gain is zero. So the input is getting amplified by zero, which means there is no output. Okay, so low frequencies aren't getting through. And then if I look at this in terms of high frequency, well, this capacitor becomes an open, which means it's just not there anymore. And so we just have the normal configuration of R2 and R1 for an inverting op amp. And so the high frequency signals are just getting amplified by a normal non-inverting op amp. So this would be a high pass filter that has gain. Low frequencies are not getting through. High frequencies are getting through, and they get a gain of minus R2 over R1. So let's go ahead and dive in and get the transfer function again to kind of verify this. So we have 1 over SC here. Now the transfer function here is a little bit, I wouldn't say more challenging, there's just a little bit more algebra that we have to do than when we did the low pass. And again, of course, we make the input the delta function, so I can just find that my transfer function is just my output. But before I do this, I'm going to kind of look at this Z2, or not Z2, I'll call it's ZF at S here, because these are in parallel. So the way I'm going to combine these in parallel is do this 1 over SC times R2 over 1 over SC plus R2 to combine them in parallel. And then I'm simply going to just multiply by SC over SC. And then if I do that, I get here that ZF is simply R2 over 1 plus SC R2. So then my gain, my transfer function is simply minus R2 over 1 plus SC R2 divided by R1. And then just rearranging some things here, we could rewrite this as minus R2 over R1 times 1 over 1 plus SCR2, but remembering that we don't really like to have this written as S times something, so we're going to, factor that CR2. Actually, what I'm going to do, factor it, or you can think about what I'm going to do is I'm going to multiply both the numerator and denominator by 1 over CR2. wind up getting then for my transfer function minus R2 over R1 times 1 over CR2 over S plus 1 over CR2. But then let's look at this again here. This form is A over S plus A. So this is a high pass filter with omega C being A. So my omega C is 1 over R2C, or if we wanted to write this in terms of hertz, it'd be 1 over 2 pi R2C. But then again, what do we have here? We also have gain here, and so my gain is minus R2 over R1 as far as my gain. So it's the exact same story, quite frankly, as the low pass filter, except now we're getting a high pass filter instead. And we still have the same thing with the 3 dB frequencies and everything. So let's look at an example here. Let's design for a gain of -10 and a cutoff frequency, and let's just say this is going to be a high pass filter. Let's just say that the cutoff frequency here is 50 kilorads per second. Now again, on an exam or even homework assignments, be very careful to see whether you're given a specification in radians per second or in hertz, because obviously that's going to change your equations here. So I'm going to design this just the same way I did with the low pass, in the sense that I'm going to first design for my cutoff frequency, because I want to get reasonable values for R2 and C. So I'm going to first design for that. So designing for that, I would do the whole 1 divided by 50,000. And of course the calculator here, Windows is not doing what I want it to do, so 1, 2, 3. So if I do this, I believe that you get R2 times C has to be equal to 20 microseconds per radian. Let me just double check that again. Yeah, 20 microseconds per radian. And at this point, I mean, it's really kind of easy again to kind of think of some reasonable numbers to pick, and I'm just going to go with the real easy route here. Well, I should be careful here. The real easy route might be to pick like R2 being 1K, but remember R2, we have R2 over R1 as my gain, so I might make R1 a little small then. So I'll go ahead here and just say let's let R2 equal 10 kilo ohms. We're going to get a reasonable value for C then, so C would just be 20 microseconds per radian divided by 10 kilo ohms, which of course if I do that, and of course it's still not putting it in scientific notation for me some reason. I get 2 nanofarads. And I should have seen that obviously just looking at this. 20 divided by 10 is 2. Microseconds divided by kilo was going to give you nano, so 2 nanofarads. And then the last thing we have to do, of course, is design for my gain. So, well, I have negative 10 has to be negative 10k over R1, and it shouldn't be hard to see from this that we get R1 is equal to 1 kilo ohm. And then, of course, on an exam or homework even, you have to make sure, I have the circuit already drawn once, but you need to make sure to draw the circuit with the component values for your final answer. So this would be 1k, this would be 10k, and this would be 2 nanofarads. V out. So nothing really too complicated by that. And we still have the same thing with the cutoff frequency here. But honestly, I think what I'm going to do here, I was going to end the video here, but I haven't, it's only about 11 minutes here, and I only got one thing else that I really want to talk about with active filters, at least for these basic ones. We might talk about some higher order active filters, but for first order active filters, there's not much else going on here. But we want to know how to make a bandpass. Well, technically there's two ways. Cascade, low and high pass, or put 2 caps in. And what do I mean by that? Well, let's look at the first one. The first one would be so this is my low pass filter. C low. Now, actually, I'm not going to do C out there. That might get a little confusing. I will label this C1, R1, R2, and then minus, plus, R4, R3, C2. And then this is my high pass filter. Now, we have to remember here the way a bandpass filter here works. And we're going to have to look at what the overall gain here is in a second. But what do I mean we have to look at how a bandpass filter works? Well, remember, a low pass filter is going to look like this, right? And a high pass filter is going to look like this. So the overall filter looks like this here, but then let's look at these here. This omega C1 and then omega C2. Omega C1 is actually from, if I look at this here, omega C1, actually I have those drawn backwards here. This is my, I said wrong things here when I drew these. So let me redraw this here. This is my low pass filter. this is my high pass filter. I mean, the figures were drawn fine, but what I said was wrong. And then the green is the overall result. So what I want to say here is omega C1 is actually the cutoff for the high pass filter. And then omega C2 is the cutoff for the low pass filter. So what do we have here? If we look at this circuit here, omega C1 is the cutoff for the high pass filter. So this would be 1 over C2R4 because it's the high pass filter. And omega C2 is the cutoff for the low pass filter. So omega C2 would be 1 over C1R1. Okay, so those are my cutoff frequencies. So let's kind of box those. But then let's talk about the gain. Well, for the low pass filter, we have a gain of negative R2 over R1. For the high pass filter, we have a gain of R4 over R3, negative. So my total gain here for the bandpass filter is going to be R2, R4 over R1, R3. Now, to make life easy, what we often do is we would set one of these stage gains just to 1. Because if you're trying to get a total gain of 10, let's say, yeah, you could set it so that the first stage has a gain of 2 and the second stage has a gain of 5, so your overall gain is going to be 10. Or you could just set one stage's gain to be 1 and then the other stage's gain to be 10. And so we often just have these be unity gain stages for them, and then the last stage we put the amplification in. Or sometimes what we do is we do unity stages for all of them and then just put in a gain stage at the end. Now there is another way to design this here, and this is, let's look at this here. We've got 1, 2, 3, 4, 5, 6 components and 2 op amps. Now another way to design this here, and you can do this with a single op amp, and 4 components. This actually works as a bandpass filter because right here, this is my low pass filter, omega C, and then right here is my high pass filter, omega C, and then I know it's kind of messing the diagram up a little bit. I have my gain sitting in there. Now the disadvantage to this is sometimes with all the things you need, like the gain and the high pass and the low pass cutoffs and everything for the band pass, it's not very efficient or feasible to do this, but it is something you can do here. And so let's go ahead and write the equations down here. The equations for this would be, in this case for this filter, the gain is just simply minus R2 over R1. And that's a bandpass filter, so omega C2 here. Now I got to be careful. Remember, omega C2 is caused by the low pass filter, so this would be 1 over R1 C1, and omega C1 is caused by the high pass filter, which is 1 over R2 C2. Now, remember here, and I'm not going to go through an example because really at this point it's just a bunch of equation plugging chug, but remember here that there are 5 parameters for a bandpass filter. So we have omega C1, omega C2, omega naught, which is equal to the square root of omega C1, omega C2, the bandwidth, which is omega C2 minus omega C1, and the quality factor, which is, I'm losing this for a second here, omega naught over the bandwidth. Sorry about that, it took me a second to remember what the formula was. So we have 5 parameters for the bandpass filter here. And so if you're given a design for a bandpass filter, remember for what we've talked about with these active filters, for the active filters, you want to design using omega C1 and omega C2. So always find these. Because remember, if you're given 2 parameters, you can find the other 3.